Okay, so hopefully everybody got a chance to look at the either the book or the video for today for reactions of the Alkynes. Are there any questions about any of that right off the bat? I guess we'll have to find out that.
So, this sheet, the
Work problems? Yeah.
Right. So I think in the notes, we had, when we drew out like this, we'd switch these two.
Okay. Let's just go over.
Okay.
So we talked at the end of class about how you make a triple bond from the dibromo alkyl halide. And so the question is about the geometry. So we'll just go back to kind of where we started. And I might modify this a little bit. So in order for us to make a triple bond out of a dibromo halide, we need to make the dibromo halide first. And so the way we make that is by taking a double bond and reacting with bromine. So then we have to go back to last semester and we have to say, okay, you're going to add a bromine to a double bond. What two atoms am I adding? Two BRs, Markovnikov, anti-Markovnikov, irrelevant here because of the two bromines. 100% cis, 100% trans. Because it goes through the triangular bromonium ion, it's going to be 100% trans. Now, the problem when we make this product is that it's acyclic, so there isn't really I can write it like that to imply that they're trans, but since there's free rotation around the double bond, I could put the bromine here in any of the three positions just by rotating it. And this is a Lewis structure, not a three-dimensional structure with bold and dashed wedges. So then if I'm going to do my first deprotonation, I'm going to use NH2-. And it really doesn't matter whether I deprotonate at the end or a hydrogen in the middle. What's important is that the hydrogen and the bromine are trans to each other. So when I did this probably on Monday, I just said, okay, let's deprotonate one of these hydrogens and then deprotonate the bromine, and I didn't explicitly show that they were like trans. So here's what I'll do. I'll change it like that. So now that comes in, the base comes in, grabs that hydrogen, that pair of electrons goes there, and that bromine gets kicked off. So what's important is that the hydrogen and the bromine are trans, but this is the best way I can show that happening in this Lewis dot structure.
Wait, so the bromines like that are still trans to each other?
No. But what I had to do in order to do the second reaction is I had to freely rotate around the single bond to put this hydrogen then trans to the bromine. So that's why this is an acyclic system, is because the bromines originally went in trans, but then there's free rotation. But for this part to work, I have to have this hydrogen and that bromine trans. And that's the problem. If I would have showed it originally this way, you would have said, but you didn't write the bromines trans. I did. And then I rotated by erasing to now make this hydrogen and that bromine trans for this step. Okay, so then we have to make sure that for our second step that we've got a hydrogen. Oops, sorry, that bromine's gone. So we have to make sure that in our second step that our bromine and the next hydrogen that we're going to remove has to be trans. And so I have to write the geometry like that. And so then in the second step, the NH2 minus is going to come in and grab that hydrogen and kick that bromine off. Then we're going to form the triple bond. Okay. So in each one of these steps, and when you're showing it in the homework problems for next Friday. For the homework problems for Friday, you want to make sure that you're just showing the hydrogen and the bromine being trans.
So if the bromines are on the same carbon, like in that second problem you asked about, will we have two products then?
Well, we'll do one. We'll do one like that. Okay. So just when you're writing your reaction and your transition state for these, just make sure your hydrogen and your bromine are trans to each other, even if it involves a fake rotation that you're not showing on paper. In reality, it would all work, but we just want to make sure we show that. So this is one way to make the triple bond, quote, from scratch, meaning that I'm going to take the double bond and brominate it. This is called a 1,2 dibromide. It is also called a vicinal dibromide, and I'm not sure that I said that this morning, or I know I said it this morning. I don't know if I said it on Monday. So vicinal just means that the two groups are next to each other. The 1,2 is relative numbering. It just means that they're next to each other as well. Okay, so that's a vicinal dibromide. This one, with the bromine attached directly to the double bond, is called a vinyl bromide. So there's vicinal, which means the two groups are next to each other. Vinyl, which means that the group is attached to the double bond. And then there'll be a third one, which is the one where the bromines are attached to the same carbon. And so if you've heard, I have to take this little deviation here. If you've heard of things like vinyl, right? Vinyl, like 1980s records, is vinyl, but they're vinyl because they're made out of what's called polyvinyl chloride. Vinyl chloride would have a chloride here, and then you make a long chain polymer. Polyvinyl chloride becomes PVC, which, if you've ever seen PVC tubing, the white tubing that's like under your sink maybe, or that's polyvinyl chloride. So the vinyl term has made it did make its way into the popular words, not so much anymore, although they're making a comeback. Albums are making a comeback, but they still don't sound very good. And I know I have a 1980s stereo. I got rid of the albums, and now I'm slowly but surely getting them back $1 at a time. Somebody said, I was at a store, and somebody said, oh, these are great. And I go, yeah, no, they weren't always that great sounding. So anyway, that's where vinyl comes from. We have one more that we'll do in the next one more terminology. So vicinal turns into a vinyl dibromide and then a triple bond. Okay, so make sure your hydrogens and your bromine and these double eliminations are trans. Josh?
You said that the vicinal the bromines need to be attached to adjacent carbons?
Yes. This is also the one that's called a 1,2 dibromide. The 1,2 is a relative numbering scheme. It just means they're next to each other. So vicinal always means they're next to each other. Now, the other way to make a triple bond is to make a molecule where you've got both of the bromides. I mean, you could do this with the chloride too, but that's typically not what's done. The other way to make a triple bond is to make it from what's called a geminal dibromide. And so when both groups are attached to the same carbon, that's called geminal. We'll talk in lab when we're talking about NMR spectroscopy here in a couple of weeks. We'll talk about geminal hydrogens, which are the hydrogens attached to the same carbon. So when you make a geminal dibromide, it is possible to make two different products. Because what I'm going to do is I'm going to still react this with two equivalents of NH2 minus. And if we go and talk about, that means we're going to do two E2 reactions. We still have our alpha carbon with both bromines. We have two beta carbons along with two sets of beta hydrogens. Now in this case, we could get two possible products, right? Because we could remove, let's call these ones A, and then let's call these beta hydrogens B. If the base comes in and grabs both of the A beta hydrogens, I'm going to form a triple bond that is internal. So that would be the product if the NH2 minus grabs both of the beta hydrogen A's. And then I would form the terminal triple bond if we grabbed both of the beta hydrogen B's. Okay. And the reality of this is, so let's say these are both possible products, which they are. Again, E2 reactions, first thing, find the beta hydrogen, find all the possible alpha hydrogens, beta hydrogens, and make sure those beta hydrogens can be antiperiplanar. So in this case, well, let me ask you, which of those two products do you think is going to be the major product? A? Anybody want to go for B? No? Why A? Somebody said A.
There's more substitution.
Okay, it's more substituted, which means it's more stable. And what about NH2 minus in this process? It usually forms the more stable product. Why? Because it's not sterically hindered, and because it's not sterically hindered, it can...
They can do both SN2.
No, NH2 minus doesn't do SN2. Remember, we chose NH2 because there's something about it that only does E2. So because it's, what did we say that it is? Because it's not sterically hindered. What about that? It can get to both sets of hydrogens nearly equally well. So it can get to A and B hydrogens nearly equally well. And so what that means is that in the end, what's going to be the major product is the most stable product. When we use tertiary butoxide, remember, so this is driven, so NH2 minus gives the most stable product because that's what drives the reaction. When we use tertiary butoxide, what drives the reaction is the difference in transition states. So if a tertiary butoxide tries to grab a hydrogen that's sterically hindered, it has a huge transition state energy, versus if it's something it can get at to easier, it'll have a lower transition state. So kinetically, it'll form the least substituted product more. Just remembering that from last semester, or earlier, depending. So I would expect then that this would be the major product. And if I wanted to form product B, then I'm going to have to search a sterically hindered strong base that's strong enough to do the second elimination. My choice in that would be to say, okay, N minus is strong enough to do the second step. So how about I take my N minus and maybe I'll add a couple of isopropyl groups to it and make it sterically hindered. So that now it would force it to only deprotonate or to favor B's instead of A's. And I would choose, and you might say, well, why not put two tertiary butyl groups on the nitrogens? I don't know actually if that compound exists, but I do know this one exists because this is called diisopropylamide. It may be in your textbook from last semester as an alternative to terse butoxide with a lithium counterion, because this is called LDA. So we can take our usual approach, which is, if we want to only remove hydrogens that are less sterically hindered, make the reagent sterically hindered, is the way that we do that. But we're just going to use NH2 minus. Okay. Now the problem with making a triple bond out of the geminal dibromide is, how do you make the geminal dibromide? Anybody got any ideas? So if I said I wanted to make that geminal dibromide, how would I make it? Need a hint?
Would you make it from an alkene reacting with HBr?
Well, you said alkene, right?
Yeah.
How about if I'm going to react it with two HBRs, I'm going to need not an alkene, but an alkyne. So what I actually am going to need is I'm going to need that alkyne, and then add two equivalents of HBr to that. This was a reaction for today, right? In all the reactions of triple bonds that were in the notes in the video, this was one of them. I imagine I kind of blew through it really quick on the video because it's a triple bond plus HBr. So when I would ask you, okay, let's add one HBr to this. Alkynes, unfortunately, are just like alkenes. So what am I adding to the triple bond? H and Br. How? Markovnikov or anti-Markovnikov? Markovnikov, 100% cis, 100% trans, 50-50. 50-50? Because this goes through a carbocation intermediate, right? So if I added one HBr, I would end up with adding the Br here and the H there. It actually wouldn't matter whether it was 50-50, I get the same product either way. If I had the H and the Br cis or trans, get the same product. But it does add 50-50 because it's a carbocation in the intermediate. And then how would I get from here to here? Same thing. Now I add an HBr. Now we're back with alkenes, which one would think would be better, except that there's a month plus in between that when talking about that and now. But HBr, adding HBr, Markovnikov, 50-50. So the difficulty here in making the geminal dibromide is you make the geminal dibromide from a triple bond. So you're making a triple bond from a triple bond. And that, I don't know, that seems like kind of a waste of time. You need to start with a triple bond, convert it to a geminal dibromide, and then make the triple bond again. Well, why? So this is a way to make a triple bond, but making that compound required a triple bond to begin with. That's why it's not a great synthesis method. Okay. So, any questions about? So this, what I'm doing here is I'm tying that back to, this was a reaction for today. Right. Any questions about any of the other reactions for today? Because otherwise I'll start doing this. I'll start saying, okay, no, I won't. I'll do this. Actually, what I would have done is I would have done the reaction from before and said, how do you go from a triple bond to a geminal dibromide? And it would have been 2 HBRs. I could do 2 BRs twice, which will put 4 BRs on there. So, what's the product of this reaction? All right, let's go back to the basics. Triple bond plus H plus H2O. What am I adding to the triple bond? What two things? H and OH. How? Markovnikov, anti-Markovnikov. Markovnikov. H and OH. Markovnikov. Doesn't look like it matters whether it's cis-trans or 50-50, but what is it? 50-50? Why? Because it says it. That's not going to get you any points on a test. Because it forms a carbocation intermediate. Maybe I should write that out. Didn't I at some point? Okay, so remember that the first step in this reaction is to take and add the H to the carbon with the most hydrogens, and then that would make that carbocation. That's called a vanillic carbocation, because anytime you get the double bond involved in something, it becomes vinyl. So that's a vinyl carbocation. Not particularly stable, but it does form. So then what would we do? Then we would add our H2O to that double bond. We would form then an oxonium ion, and then with the double bond, and then I would lose my H plus to get me to that molecule. And if I get the sense that we need some practice on this, then I'll create some of the homework problems to give us some practice on this, just so you know I'm getting that sense that we might need to write a couple of mechanisms here. Great, is this the final product? No? So what is the final product? What functional group? A ketone. So this is not the final product, but the first step makes sense with what we learned about last semester with alkenes. And one of the things is, if I keep saying about the alkenes, and if you're going, I don't remember much about the alkenes, number one priority is go back and look at the alkenes and remember what we did. So the final product's the ketone. So I will come over here and I will write that product again. Only I'm going to move the OH there. What is this molecule called? An enol. Why is it called an enol? It's half alkene, half alcohol. So it's an enol. Is it stable? Simple ones are not stable. There are some that are stable. If you go on and take PChem lab, you'll actually do an NMR experiment where you'll be determining the equilibrium constant between enols and ketones, and you can determine how the structural effects change that as well as how temperature changes it. But simple enols like this are not stable. I think somebody actually has isolated something simple like this, and it was a fairly big deal. I think if I remember who it was, I think when I was a postdoc, he might have sent stuff to my lab and said, can you make a little tiny crystal out of it so we could figure out the structure, and I failed. But somewhere along the way, he was able to get it to be stable enough at least to get a structure on it. So the enol then is not stable. So what does it do? It undergoes an equilibrium, which is called tautomerization. And tautomerization is when you basically move a hydrogen and an electron pair or electron pairs at the same time. So it's a simultaneous movement of hydrogens and electron pairs. This is not forming a resonance structure, because the rule about forming resonance structures is you're not allowed to break bonds. And this process breaks and makes bonds. Okay. Dr. Weiner and I published a paper on this, and we had to remind the referee. He said, well, this resonance. And we're like, no, that's not resonance, that's tautomerization. Hopefully you're not angry and we'll reject our paper because we're correcting you. Which they didn't. It took them a little bit longer. But so tautomerization, it looks like resonance, but it's not. So what happens? This pair of electrons moves here to form the carbonyl. The carbon-carbon double bond breaks and it goes to form the CH bond. So this hydrogen, I usually put a square around to show where it's going. It's going from being bonded on the OH to being bonded on the carbon. So the final ketone product will look like this. the box moving. And so when you hydrate an alkyne, you're going to end up with an alkene if you do it by Markovnikov addition. You're going to end up with a ketone. So most of the reactions that were on the additions in the PowerPoints were just extensions of last semester. Adding an HBr Markovnikov, or adding 2 BRs, and then adding another 2 BRs. Or adding HBr anti-Markovnikov. Oh, that's the one I was going to ask. If you wanted to go from, if I had this alkyne and I wanted to go and form this double bond. Adding the H here and then adding I'd form possibly 2 products. So if I wanted to do this reaction and add the HBr anti-Markovnikov, what should I add? HBr and what's your sheet say? ROOR or H2O, HOOH. Right, I need the peroxide in order to make the reaction go anti-Markovnikov. I would refer you to the alkene reactions because this is how we make the reaction go anti-Markovnikov. It will be 50-50 because this goes through a radical intermediate. However, of product A and B here, which one do you think is going to be the major product? Do we agree with A? You have more than one head nodding, so you're okay. You're not on your own. Anybody want to go for B? Anybody want to go for I don't know why? Or which one? Why'd you say A, Ariana? Change that to something that starts with S. That was a question. Which one's more stable? ST. Steric hindrance, which is the same thing as electron density. So in other words, having these 2 groups, trans is more stable than having them cis. And since when we make a radical, there's going to be the ability to form 50-50, it will form probably a major product of A, but you're still going to form A and B. And notice that I haven't used a couple of sets of words from last semester yet that end in selective, right? Stereoselectivity versus regioselectivity. I haven't used those terms. I could, but I choose not to at this point. So, a couple things about this. This semester is a little bit, it has more challenges than last semester. Right? I could say it's harder. Okay, it's harder. The reason, 2 reasons. Number one, because we're doing reactions, which we only did at the end of last semester. So we're learning how many reactions a day. A lot, sometimes. Not only is it important to be able to write the product of the reactions, but it's also important to remember what reagent you need to use. So you kind of have to not only be able to write the products, but if I gave you the products and the reactants and said, what reagents do you need to use? You have to remember those as well. So in this case, what you do is you'd say, okay, what's different? Well, it looks like I've added an H and a Br. All right, how do I add an H and a Br to a triple bond? HBr. How did I add them? Anti-Markovnikov, I need the ROOH. Okay. And so there's lots of ways, well, ultimately you have to come up with a system in order to get those reactions in here and keep them here for the rest of the semester preferably, but long chunks of time at least. And one of the ways you can do it is by summarizing them on a piece of paper. You could make 3x5 cards. My suggestion, if you're going to make 3x5 cards, is number one, start now and go backwards to all the reactions we learned last semester. But when you're making maybe a 3x5 card, what I like to do is, well, let me make the 3x5 card out of the screen. So for that reaction, what I would do is I would do this on the front. I would say something like that. Okay. And then on the back, so that's on the front. On the back of that card, I would write this. I would write the reactant and the product. Now, the reason that you can do that is because when you have a stack of cards, and you can imagine just how quick the stack's going to go right now, like you might have to spend $2 or $3 at the dollar store on 3x5 cards, and they're like $100, so that's like 300 cards. That might get you through the semester. You're going to put other things on there. But if you have a stack of cards, then you can not only say, okay, get practice writing the product, but then you can also turn them over and kind of remember what the reagent is as well, so you can use them both directions. But ultimately, how you put those together is your system. And I don't mess with student systems. If you have a system that's successful, I don't mess with it. Right? I had research students, she's like, don't mess with my system. Didn't mess with the system. After I was told that like 3 or 4 times. So, but ultimately you have to come up with a way for you to remember this. And so if you're going to do 3x5 cards, or if you're going to do it on the computer, because I think there's flashcards you can put on the computer and stuff, try and remember both ways, because we're gonna want to do this kind of stuff. And the reason we're going to want to do that is because organic chemists make things. That's the job. Some of them make plastics or polymers. Some of them make drugs. Very rarely do they ever make a reaction in one step. They never make what they want in just one step. They always want to do probably anywhere between 10 and 26 steps. So they're constantly turning A into B and B into C and C into D down the line of the alphabet. And so if you're thinking about making a molecule, one of the things, for instance, if I said, make this molecule, you'd go, okay, well, how do I make a vinyl, or how do I make a vinyl bromide? And then you'd say, well, I make that from a triple bond. And so then you put your triple bond and you try and remember what reagent you would use. So ultimately, we will probably not get much past letter F in this class, but still that's more than B. So we have to begin to think about how do I sequence these reactions to put them together. And So that's one of the reasons why we have to remember the reagents as much as remembering the reactant or the products. And my last suggestion for anything you do, when you're quizzing yourself, write the answer down. You know, if you got to get a little whiteboard or if you have to get scrap paper, write the answer down, because you will convince yourself that you're getting 100% very quickly if you're just doing it in your head. I mean, it's very easy to be overconfident. Write it down and then get practice that way. As if I'm not going to give you enough practice problems, or there aren't enough available, but that's the way you want to think about these things. So that's just my suggestion. If you got a better suggestion, use it. If you got a super good one, tell me. But we have to find a way to remember these reactions. Right, so that's my sort of study skills section of the. One of these days we may talk about study skills, maybe after the first test. Okay. All right, any questions about those reactions? So this was a unique one. You hydrate an alkyne and you make a ketone. When you first look at that, that doesn't make any sense, but it does with the mechanism of the enol. There's some others, kind of unique ones. There's oxidation reductions. I think I didn't get to the reductions this morning in class. And for my own sanity, I try and keep things relatively the same in both classes, because otherwise I'm going to say, remember we talked about this on Wednesday, and it was in the 8 o'clock class. I told the 8 o'clock class this morning, I said if I do that and I say, remember when we talked about this and we didn't do it, then say, hey, we didn't do it in this class, because that's going to happen. Like I said, everything's sort of organized right at the moment, but that's going to just be destroyed very quickly. So in terms of oxidation, remember that when we're talking about doing an oxidation reaction on an alkyne, there's a couple of ways to do it. We could add like OHs, or we could cleave. And when you say, okay, well, we're going to cleave. So I want to cleave this triple bond. And if you remember when we did cleavage last time, what we did was we erased the double bond, and then we converted each of the two carbons into carbonyls. I'm saying it that as if that just poof comes right to the top of your head. Hopefully it will. If it doesn't. But if you remember, we used ozone to do cleavage. We did KMNO4 with acid to do cleavage on alkenes. So you might say, well, cleavage is going to be more difficult with a triple bond, or it's going to be maybe harder to learn, and that's actually not the case. So if we think about this, it's going to be harder to cleave a triple bond than it will be to cleave a double bond. Because a triple bond's got 3 bonds versus a double bond just having 2. So that means that something like ozone won't touch a triple bond because a triple bond is too stable. So I need to use my harshest oxidizing reagent, which is KMNO4 and heat. Well, our difficulty with ozonolysis and with the KMNO4 last semester was what happens when we end up with aldehydes? What happens when there was a hydrogen over here and we ended up with an aldehyde? Did it get oxidized to a carboxylic acid or not? Well, with a triple bond, number one, there's no hydrogen there. And even if there was, I'm using the harshest reagent. So that means when I cleave this thing apart, I'm getting 2 carboxylic acids, end of story. In order to cleave a triple bond, you have to use a harsh reagent, which means you'll split it apart and all you get is 2 carboxylic acids, and you don't have to worry about, did I make an aldehyde and a carboxylic acid? Did I make an aldehyde and a ketone? What did I make? You always make 2 carboxylic acids. Some of the other reactions get to be a little bit, actually I don't even know that they're in this book, but I think cleavage is. There's cleavage in the video. Was adding 4 OHs in the video. I don't know if that one's in this book. Is reduction down to alkenes and alkanes in this? Was that in this video? So that we have to talk about just from the standpoint of there's a reagent that's confusing. When you have an alkyne, you could reduce it down to the alkane. You could reduce it to the alkene. And the beauty of reducing it down to the alkene is that it would be really great if I could not only reduce it down to the alkene, but I had control to make either the cis or the trans. That's going to give me, remember, I'm trying to build up tools in the toolbox to make molecules. So I can do Markovnikov, anti-Markovnikov. I can do Zaitsev product and the not Zaitsev product, the least substituted. I can make the cis alkene, I can make the trans alkene. And so I have the ability to do all 3 of these reactions. One of these is to use sodium metal and NH3 liquid, to use liquid ammonia and sodium metal. That's not to be confused with NaNH2. Because NaNH2, because I usually leave off the cations, NaNH2 is NH2 minus. So these 2 reagents are different. They're completely different. So the NaNH3 is to take a chunk of sodium metal and drop it in liquefied ammonia. And I'll look through the book. Sometimes there's a picture of that. It turns like bright blue. Not like Carolina blue, no. Carolina blue is bad. The dark blue of the other North Carolina school that I might have attended. You add it, that blue color comes from a solvated electron that's just running around. So we'll talk about that on Wednesday, because that mechanism I just showed you to make sense of how we get trans. It's not something you have to learn, but this is sort of the final steps of alkynes. So what we'll do on Friday is the practice or the homework problems that were on paper are due. And then I'll again take questions about any of this stuff, including any of the reactions of alkynes. But then I'm going to do the first few sections of chapter 14, which I think if you read through them, you may have a sense of deja vu about that, because I think there's a little bit of review, but I'll set the table on that for then chapter 14 that we'll do next Wednesday. Okay, so if you have any questions, feel free to email me. I'll set up the discussion board. If you want to ask a question by discussion board, I'll answer it. Otherwise, I'll